So welcome everybody back to these last afternoon talks of our conference. And it's my pleasure to introduce to you Hendrik Weber. So Hendrik graduated from the University of Bonn in 2010 and then went to Warwick, where he had, I think, a quite interesting time together with Martin Heira as first postdoc lecturer, associate professor and reader, before finally in 2018 he became a professor at the University of Bars. And since 2022 he is colleague of us here in Münster, and in particular also in 2022 he got an ERC Consolidator grant which fosters his research here in Münster. Before he had several prizes, the Philipp Lever-Hulmer Prize and Rollo Davidson Prize, and also from the Royal Society University Research Fellowships. And with this, we go into this talk, which is quite closely connected with the topics that we are addressing also in our cluster, with the title Noise, Differential Equations, and Quantum Fields. So it's yours.
Okay, so thank you, Mario. Thanks a lot for giving me the opportunity to speak here. I mean, and perhaps I can also say that, I mean, as I've not been in Münster for so long, that I'm really enjoying very much the atmosphere of this cluster here, and it's really great, I think, to see kind of this workshop kind of showcasing the different areas of activity that happen here. So what I want to do today is sort of a broad story of how one could use stochastic differential equation to learn things about quantum fields. But as this is a very, very broad audience here, I start with a bit of an introduction of what these noise terms in these differential equations are, and a bit of a historical overview in the first sort of 10-15 minutes. And so I start with something very classical, which is the random walk. And I mean, this is something that if you've attended any course on probability theory, you will have seen. So this is one of the classical models where you just, here's your time axis, discrete time, and at every given step, you flip a coin and you either go up with probability a half or you go down with probability a half. And that's what the formula here says. And sort of what is, again, very classical, if you look at the behavior for this process for large n, and I actually have here, you can see what it does. So this is a simulation, and I have to thank Simon Gabriel, who's sitting there, who actually did it for me. So here you see a not very interesting case where there's just a single coins, which in this case was -1, and it's connected here with a line. And now if you kind of increase the number of tosses that you should be able to do here, you will see some pattern arising, and you see however far I zoom out, at some point, I mean, of course, individually the picture changes, but sort of the global feel of how the graph, this doesn't change so much anymore. So if you go here to 10,000 coin tosses, typically you will have something of the order of magnitude of 100 at the end. I mean, that's not quite here, but let's just resample. So we can do this a couple of times, and you will see, so now it goes to +100, and it goes to minus, well, now it goes to 0, but okay. But I mean, you see that it kind of looks like a universal object that you would get in the limit. It's a random thing, but it has kind of universal statistical features, and that is, again, one of the starting theorems of stochastic analysis, the Donsk invariance principle. It tells us that we can do this, and indeed the limiting object is called a Brownian motion. And I mean, again, this theorem is perhaps not as, I mean, it's not as innocent as it might look, but it actually means that also kind of interesting path observables such as the supremum over an interval also converge, not just pointwise statistics. And so, oh wait, that's not what I wanted to do. What I wanted to do is, so the noise in these equations that we have are sort of increments of these Brownian motions. So the point of view that I would like to take is here you take an infinitesimal bit of time, and then here you've picked up an infinitesimal bit of noise here. So perhaps in slightly more mathematical terms, I would like to actually not view bt as the fundamental object, but kind of view dt as the integral over from 0 to t over something that I will call the noise. So this is white noise. And so I mean, if you want to say this somewhat more precisely, you can interpret this white noise as the distributional derivative of bt. And the first thing that you will see is, I mean, the Brownian motion itself is already quite an irregular object. And for those of you who know, this is a function which only has Hölder regularity a half. And so now we're dealing with things that are just of regularity minus 1/2, whatever that may mean. Perhaps another thing that I should highlight here, I mean, again, if you're used to PDE or so, and you're kind of used to bad solutions that are kind of have singularity at certain points, and then you want to measure their behavior near that point, but here it's really bad everywhere, right? I mean, Brownian motion is really as irregular at every point. And so this object here you can formally write. It has this, I mean, not even so formal. It's easy to interpret this. This is a delta correlated random field. So the covariance function is given by a delta function. No problem to interpret that rigorously if you just put some test functions, but it's very irregular. So it really has kind of -1/2 time invariable. And Ito calculus or stochastic analysis is concerned basically with solving differential equations which have such a noise term. So I would like to write it here. So you have a drift here, and then you have this noise. Somehow the convention in stochastic analysis goes that you use this differential form, which kind of writes it more like one forms. I must admit that I've never completely understood why that is a good idea, but I'm very happy for people who tell me. So this is this was pioneered by Kyosho Ito in the 50s. And I mean, his solution theory was based on some deep stochastic identities that actually I'm not going to use in this phrase, but I have them here on the slide. So instead of actually retelling you the story that you will have heard if you've attended any course in stochastic calculus, I want to show you an example of what actually the problem is on the next slide. So the problem here is really that this product here, or written in stochastic calculus here, is hard to interpret, because what you have is, so this noise, this we can interpret as a distribution, but we know from courses on distributions that we cannot in general multiply distributions with functions unless the function is very smooth. So we can always multiply distributions with test functions, but we cannot multiply distributions with irregular objects. And here, this object is also not so nice, because x itself will just be one derivative better than this psi, and I mean, it just about doesn't work. I mean, it's just about not regular enough. And the following example, that is from the 90s and is taken from a very nice paper by Terry Lyons, actually illustrates this, and I want to walk through this. It's very elementary, but it's explicit, but I want to walk you through it in a bit of detail, because it will pop up, something similar will pop up later. So the first thing is, so if you want to enter one mathematical representation of this object that I had introduced, the white noise, one was the limit of these random walks, or of the increments of random walks. Another one is as a random Fourier series. So if you want to have white noise on the interval 0, 1, you can write it as this series where you have Cn, this is just the cosine with the right renormalization, and Sn is a sine with the right renormalization. And then each of these coefficients here, you just choose Gaussian, so standard normal variable, with all of them are independent with variance 1. Okay? And this is also the reason for the name white noise, because I mean, white light is the light which has kind of the same amplitude at every frequency, and sort of white noise is noise where the noise level is the same as at each frequency. And so it's pretty easy to construct a Brownian motion from this just by integrating it up. So that gives you this formula here. dt is well, this is just the integral of the object above. And this sum now really converges, for example, uniformly. So there's no problem. And now let's try to understand. Now I'm going to construct a second Brownian motion and tell you that I cannot integrate them against each other. So that's as a key example for a product that I cannot define. And what I'm going to do is not so much, actually. I'm going to take this twiddle Brownian motion. It's going to be the same here. The only difference is that in the sequence here, I've exchanged the sine and the cosine. So here, the sine becomes a cosine, and this cosine becomes a sine, and I've swapped the sign. I mean, why not? And I mean, this thing is a Brownian motion, because, of course, it doesn't matter if I call them an or bn. They're all independent Brownian motions. So in law, it's clearly exactly the same object. But they're, of course, not independent. And now I want to argue that I cannot actually integrate one of them against the other one. And let's just show that. So let's see, can we define this object? And here I've just recalled, I mean, the bn was just some linear factor plus that, so I'm just going to take the gn because the calculation becomes explicit. And so how I'm going to do it is I'm going to just cut off this Fourier series at level n, and then integrate them and then see if I can pass to the limit. And again, I mean, everything is explicit, so I can do this calculation very explicitly. So the integral from 0 to 1 is just that sum over these random variables an squared plus bn squared with a 1 over n here. I mean, the 1 over n is exactly a common fact that here you had one integral. This gives you exactly a 1 over n. Whoops. And now you see that this is a problem, right? Because if you just take expectation of these things, the expectation of each of these things is 1. And then you have to sum 1 over n. So this thing actually diverges logarithmically. And this is, of course, due to the fact that I have done this change. So if I had kept my original Brownian motions, there would have been an a times b minus b, a times b minus b times a or something like that. So it would have been 0, but it would also not have converged absolutely. Okay, so this really captures the fact that these objects are, in a sense, actually too low regularity to be integrated against each other, and it's just, I mean, either you just do some symmetry or to some stochastic cancellations that this thing. So this thing is just diverges. But what one can do, and we will see this again later, is I could actually say, well, but I mean, this divergence is pretty explicit. It's just a divergent constant. Perhaps if I get rid of that average, perhaps I can do something reasonable with the remainder. And that is indeed actually true, and I'm not going to walk you through the calculation, even though it's easy. You can actually check that if you subtract the expectation of this object, then you do actually get, so you subtract a divergent constant, but you do get, once you have done that, a well-defined limiting object in L2. So it's in a sense a renormalized stochastic integral. Okay. So just to highlight the points, so this issue of renormalization that will pop up in quantum field theory later in the talk a lot. If you really make a little bit of an effort, you can make it appear actually even in classical stochastic calculus. So it's not so far out there. Okay, so this was just an aside, and we will, and more as a foreshadowing for what will come later in the talk. So now go back to sort of my history lesson. I mean, Ito calculus that Ito developed, and he didn't use this kind of approach at all. It has really many applications, pricings of options, large-scale dynamics of particle models, many, many, many. But one I want to highlight here is in MCMC algorithms. So the question there is the numerical question, is if you have a complicated probability measure on some possibly complicated space, and you want to compute the expectation of some observable with respect to that probability measure. And that's in general a difficult question of how to do that. And one very standard way to approach it is that you would just find a Markov chain, a stochastic process, a nice Markov chain that has the correct measure as an invariant measure, and then you look at large time averages. And the hope here would be that these large time averages would be sort of the same as spatial averages if you've chosen your chains in a smart way. And this is true in many cases, and in fact, these kind of MCMC algorithms that are based on that are very commonly used everywhere. And SDEs give rise to one of the very standard ones. So again, this is a very interesting special case of such a measure that you may be interested in. So you are on some RD, and then you're given a measure which has kind of this potential, and you usually only know the measure. You don't really know what this 1 over z here is, but you know this potential function v here, and you may want to calculate expectations of that thing, and then SDEs give you a convenient way of doing that. So I would say the vanilla, most boring candidate dynamics that would do what I just did is the so-called Langevin dynamic or overdamped Langevin dynamic, where you just take a gradient flow with respect to this energies here. So it seems probably plausible. So here you have, if V is large, then the probability of that set is small. So it seems reasonable that your dynamic wants to go downhill in the V. And then you have this noise term that kind of makes sure that you still do explore the whole space. And this dynamic actually even is not just invariant for the right measure. It actually has a stronger property, which is called reversible. So this means essentially if you start your dynamic in in the right measure and then run it forward, then it gives you the same dynamics as starting and running backwards, starting in that measure. So there's no net flux in that measure, and that's what's expressed in this formula. And again, I mean, an advantage of this algorithm is that you don't need to know the z because it doesn't appear in this formalism. I mean, this is so commonly used that if you look at papers on Markov chain Monte Carlo algorithms, they very often start by saying how much better they are than overdamped Langevin, and why you shouldn't do overdamped Langevin. And that kind of highlights the importance of this algorithm because it's often used as the vanilla choice that you want to do better than. And it can also be used in infinite dimensions, and that's what I want to do in the rest. So at this point, I sort of stop my history lesson on stochastic calculus, and I'll do a step back, and I want to go to this second topic of the talk, which is this thing with field theory. And I'm certainly not going to try to give an overview on field theory because, I mean, I'm sure there would be much better people than me to try to do that. And also, this wouldn't be the scope of the talk. And also, sorry, yeah. So wait, I'm too quick. But just like a couple of key words for that summarize some things that perhaps is good to know for the talk. I mean, so quantum field theory was developed. First theory, quantum field theory of quantum electrodynamics, was developed to understand nature at the smallest scales. And for example, the standard model of particle physics is the quantum field theory, and it's highly successful, tested to extreme precision, but mathematically incomplete. So to date, to the best of my knowledge, there's no rigorous construction of a field theory of a non-Gaussian field theory in this physical four space-time dimension. And prominently, there's this Young-Mills-Clapeyron problem that is dealt with exactly to construct such a theory in 4 dimensions and to establish that spectral gap property. So this is, I mean, certainly not something we want to approach today, but kind of examples that were treated in the past. So one possible approach to construct quantum field theories leads actually through the construction of probability measures, I mean, suitable probability measures on spaces of distributions. And one class would be kind of measures that are formally of that form. So you have your distribution here, and then you evaluate some action, and then you kind of integrate against Lebesgue measure on the space of distribution. So this is a purely formal expression. Basically, none of the terms here make sense. But the way you have to interpret that is that you discretize it, and then when you take a lattice, and then you kind of also take a large-scale cutoff. And for every such cutoff, then this Lebesgue measure makes sense, and you take an approximation of your action, and then this object actually makes sense. And the question is that you then want to have to take limits where you remove the grid and also go to infinite volume. Oops, this is really dangerous here, sorry. Just to say, sort of examples are, the easiest one is this free field here, where you have such a purely quadratic action here. And then perhaps slightly more interesting here is this 5 to the 4 theory, where you have a quartic interaction here. But I should also say, sort of perhaps from the physics point of view, these are easy or boring theories. So I think you go to a course on quantum field theory, they will look at much more complicated theory typically and not worry so much about the existence. But these are relatively easy. Well, from that point of view. And so let me perhaps just say a few words on the free field. So the free field here, which corresponds to this quadratic action, that's actually easy to construct and to analyze. And what you can actually do is you can write it down if you kind of, for simplicity, put yourself on the torus. Then you can just write it down as a random Fourier series, and it's really as explicit as it gets. So you just take these trigonometric polynomials, you take Gaussians of amplitude 1, they're IID, except for that you want them to be, you want the field to be real valued, so you want to have xi to be the complex conjugate of x minus I. And then you take this 1 over k squared in front here, which corresponds to this Laplacian operator here. And you should also, perhaps, if you remember the formula that I showed you for Brownian motion a couple of slides ago, you should also feel very strongly, I mean, it's very, I mean, okay, there I wrote it not with trigonometric polynomials, but with sines and cosines. But essentially, it's the same thing. So the Brownian motion in one dimension is basically the free field in one dimension, except for this m squared term, which I didn't have there. But anyway, I mean, this sum, you can always write it down. You can write it down in any dimension, but it will be very irregular the higher you go. And you can actually do this calculation if you calculate, for example, a fraction, an HS norm, so an L2-based Sobolev norm, which by definition is just the sum here with these weights. Then an explicit calculation just tells you that this thing is finite whenever the regularity is less than 2 minus d over 2. And I mean, let me just show you this on a table, what this amounts to in one dimension. So this is regularity a half, and that is exactly the half regularity that I'd shown you for Brownian motion. In 2 dimensions, you're already a distribution, so this is below 0. In 3 dimensions, it gets worse, so minus a half. So every extra dimension costs you half of a derivative. Okay. So this object is fine. I mean, it's irregular, but it's no problem to write it down. And more interesting it becomes when you add nonlinear terms here. So this is here, this 5 to the 4 theory, which differs from the previous one just by this extra term. And I mean, this 5 to the 4 theory is really an extremely much studied theory in mathematical physics. So before I go through this discussion here, let me perhaps show you this quote at the bottom, which I find really funny. So there's a paper from the 80s that I read on renormalization group construction of this 5-4 theory. And in the introduction, there's the sentence, the Euclidean 5-4-3 field theory has become a mature branch of mathematical physics. So, I mean, it should perhaps tell you something about a problem if a problem itself has become a branch of mathematics. So anyway, so it has been treated for a long time. In one dimension, there's not much to say. It's not so it's just there. And then the construction in 2 dimension was done in the 60s, and then very famous work in the 70s by Glim and Jaffe. And very recently, I mean, this is again something that has been conjectured to various degrees for a long time, but from dimension 4 or higher, there is actually no reasonable theory here, in the sense that, and the theorem that was proved a few years ago by Eisenman and Dominel-Copin tells you that any reasonable approximation to this theory that you may want to write down, if it converges, the limit will always be Gaussian. And that's, in a sense, that's trivial from the point of view of quantum field theory, so it's not interesting. But so this still remains one of the, in terms of like positive constructive field theory, this remains one of the classical important results. And generally, I mean, this theory has stayed very much a test case for new methods that people were developing. And so now I want to spend a moment to connect this the story of stochastic quantum field theory to the story of SDEs that we had before. Oops, what happened now? Somehow the computer, there it's back. So there is influential work from the 80s already by Parisi and Wu, and also kind of at the same time from the MCMC community, who proposed to look at Langevin dynamics for these Euclidean field theories. I mean, these are just complicated probability measures on very high dimensional spaces, but why not? I mean, let's just do it. And I mean, it's actually interesting. These papers came from very different motivations. So here, I think this was really an honest numerics paper. So they really wanted to run the simulations and just get samples from this. And Parisi Wu were motivated by some slightly more complicated problem in, well, it's called, it's motivated by gauge theories and the problem of gauge fixing. But I mean, anyway, so they proposed this, they proposed to look at this thing. And if you write down what this Langevin dynamic would correspond to for these theories, you end up with a stochastic partial differential equation here. So you have here this term would correspond to this gradient of this action that we had seen before, and this would be a white noise now. And this is now we had seen before. I told you what a white noise in time is, but this would now be a white noise in d+1 space-time dimension. And I mean, again, this theory has been looked at. It was proposed in the 80s, and there were attempts to develop such a theory for these equations and for these MCMC things in the 80s and 90s. The resolution only in 2D came only in 2002. So it's even in 2 dimensions, from the proposition and the good solution theory, there was really 20 years. And sort of the big breakthrough in this whole field of these kind of equations came around 10 years ago with Martin's work here on regularity structures. So what that theorem said is a short time well posed in this theory for the stochastic quantization equation for this 543 equation. So roughly speaking, the statement says that if you regularize the equation and you put the right counter terms, and these counter terms have very much the same flavor of this infinity that I subtracted in my renormalized stochastic integral a couple of slides ago, then up to a random time, these phi epsilon actually converge to a non-trivial limit. And I mean, at the time, it was kind of pressing from the beginning that short time was perhaps not sufficient. You wanted to go globally in time, and that was, I mean, I did this with Jean-Christophe a couple of years after. So we developed this global solution theory on the torus, and then in the years kind of after that, this was extended further to the full space by Gubinelli Hoffmanova and by a student and me. So I want to actually now take I think like 10 minutes or so to actually explain to you the theory of regularity structures on 2 slides. So let me do that. Yeah, that's right. So I'm not going to do this for 5.4 because it becomes notationally a little bit more complicated, but I'm going to look at that example here, which at least in terms of the length of the formulas is easier, not really mathematically. So this is what in this business is called GPAM, or generalized parabolic Anderson model, and generalized because the usual parabolic Anderson model would have a linear u here, and it's now a g of u. And I'm going to look at this on the 2-dimensional torus, and I'm going to look at the case where psi is now only a spatial white noise, so this will only depend on the x variable, and I'm going to have it constant in t. And this is sort of the first example that people looked at in this theory, so it's a really good toy case to look at. And so the usual business problem that people have in this business is that you would like to say, well, this psi you can calculate its regularity. It's just below -1. In the same sense, I mean, the way it goes here is that every extra dimension costs you half a derivative. We had seen before that white noise only in time has regularity -1 and -1/2. And of course, I've not told you what negative regularities are. And here we're in 2 dimensions, so we have regularity -2, -1. And so if things were good, if I had a solution theory, then u should be 2 derivatives better by Schauder theory. And then this should be in C alpha, so this would be just below 1. And then the power counting problem is that I have, I mean, the rule of the game is here. You can always multiply functions if their sum of their regularities is positive. And this just about fails. So this is a good example because it's sort of the borderline case where you have to think of something else. Okay, so there is no analytical solution theory for this equation, and that is just the same as for 5.4, where you want to cube a distribution of negative regularity. So the problem is really exactly the same. And now we're going to have to look at the renormalization of this problem. And so this problem stood for a long time, and the ansatz, I mean, this is really now turning a bit into a PDE lecture, so sorry. So what one does is actually intuitively, I think, relatively easy. One picks a base point here, and you say, well, if you're only interested in what the solution does near that given base point here, then you might as well replace this variable coefficient thing here by the frozen coefficient at that point, and then you have an error here. I mean, arguments of this type we have seen before in talks. Today, I think Katharina Schratz said something a little bit like that, I think, if she's not here. Anyway, and so this is, I mean, also if you've ever seen a regularity theory for non-constant coefficient equations, that's what one does, right? So this is not such a standard, not such a complicated thing to do. And now you have these frozen coefficients. So here I've just repeated the frozen coefficient equation, but that suggests that if I'm only interested in what the solution does near that base point, then I might perhaps to leading order be able to disregard that term. And that suggests that the solution should look on small scales a bit like the solution of this one, but this is now very easy to solve because this has a constant coefficient, and now I can just solve the equation with a constant coefficient noise. Okay, so from a complicated nonlinear problem, I have just at least locally reduced it to a very simple linear problem. So this is this notion of modelledness. This tells me that that here is now the solution of the heat equation without a coefficient in front, and I mean this is of course linear in this expression. So this the freezing of coefficients suggests that kind of the near that point increments of that point should look like basically modulated versions of this much simpler linear object. Okay, and this is an object that we know absolutely everything about. So this is just white noise, and I solve a heat equation with a white noise. This gives me a Gaussian object. I can write down covariance functions. I can write it down in Fourier space. I can write down whatever I want. And so it seems now a relatively reasonable working assumption that here I actually now get locally, to leading order that would dominate the behavior. And so now if I want to understand what this product does, u times xi, or more generally g of u times xi, it should actually suffice, because the kind of the worst behavior near that point is given by this z, that I can define this z times xi. Okay? And I mean, this is sort of the whole gain of this business, because before I had to multiply a general, very complicated random function here, and now I've reduced the problem to multiplying two very explicit Gaussian objects. And again, this can be done by writing down in Fourier space what I have done. And I mean, I'm not going to do this here, but the calculation is essentially the same as the calculation for Brownian motion that I had done a couple of slides ago. Okay, and again, you have to renormalize it with a logarithmic term, but it's the same. So this is the basis of the local theory, this idea that one can do this, and I mean, this has been now done for a very broad class of equations, but this global problem still remains very interesting. So it's been resolved, as I had showed you on a previous slide, for this phi to the 4 equation, but there's still many problems where this is not very well understood, and I want to now just kind of to end this presentation, show you 2 slides where I show you one very recent result on the spirit, and one as a warning sign, something where this can actually go wrong. And the first one, okay, this is the first one. Oh, yeah, I'll go to that first. So the first one is just a very recent result I want to advertise a bit. So there's, if you're interested in more details on this, there's a poster down there which my student Guillaume Feltes, who's sitting there, has presented, and I'm sure he'll be happy to tell you more about this results. So this is again this GPAM equation that I had shown you before. So there's again, I mean, we deal with a case where this is for example white noise in space, but it's a bit more general as possible. In this case, the solution actually itself is a function, so I can allow for nonlinearity applied to it. And I mean, this is actually interesting because this was, in a sense, the first equation that was written down with this theory. I mean, if you look at the first paper that Martin wrote on the theory of regularity structures, there were 2 examples treated there: this one and the phi-4 equation. But even with extremely nice coefficients here, so g, g prime, and g second are all bounded uniformly, say by 1. Actually, the non-explosion of this was open. It's very easy to prove non-explosion if u is linear, which in a sense is the most interesting case, where this covers this PAM, but also relation to the KPZ equation. But still, it was very unsatisfactory that for nonlinear g here, this was not known. And I mean, now just a few weeks ago in a preparatory result, we've been able to resolve this at least for a certain parameter range here. I mean, I don't want to go into this too much, but yeah, I mean, we're quite happy with this result here. Again, I'll refer to Guillaume, who's happy, I think, to explain more details with his poster downstairs. And as a last point, I want to actually show you another example, which is not due to me, but actually I learned this in a paper by my colleague Arnulf Jensen here from a couple of years ago. I'm not sure if Arnulf is here, but so this is something I like very much, and it shows what can actually go wrong in this theory. So we understand now very well. I mean, again, this example came when I learned about it. It came to me a bit as a shock because I came from this rough path theory framework where I thought, well, I mean, the problem in stochastic analysis is these small frequencies, and once you those can be kind of controlled with local expansions, a bit similar to what I've shown here. And once you've done that, then everything is good. But this example shows that actually stochasticity is also really important in this low regularity case for large-scale behavior. And what is done here is so you see this is an ODE which just, if you didn't have noise, just goes around in circle. Okay. So if you ignore this thing here, you have just an x to the m. So kind of the further you are out, faster you spin. So the time that it would take to spin at radius r goes like r to the minus m. The time goes like r to the minus m. Yeah, that goes like r to the minus m. Yeah, that's correct. But I mean, this spinning thing certainly doesn't want to explode, right? I mean, this turning vector field has absolutely no reason to push you out to infinity. And now if you add this forcing here, let's say a Brownian motion, why should it make things explode? I mean, the thing is then, and if we have a little bit of regularity of this W, there's absolutely no problem to show that this thing doesn't explode. And what this very interesting example shows is that I actually, if I'm too low in regularity here, I can actually construct W here that make this explode. And so what the precise statement is if you choose m large enough, then there exists an alpha and a Hölder function of that regularity that depends on the initial data. Such that then this equation actually blows up in finite time. So I mean, again, I think it's kind of a cool effect that you have something where kind of this term by itself wouldn't blow up, this term by itself would certainly not blow up, but they interact in a way that it does blow up. And the example is actually, I mean, this is not exactly how it's written down, but in spirit, how it works is actually quite nice. So you would just say, well, this dtw should just be the solution x to the epsilon times x. And I mean, then if you plug that in the equation, then this is just a drift always outwards that is clearly superlinear, and that's very easy to see that it makes it explode in finite time. But then due to this very fast rotation, then if you integrate it up to go from x to w, then you have such fast cancellations that this function actually becomes alpha Hölder uniformly. So this is, I think, kind of a cool effect. And there's also very recent forthcoming work by people in Berlin who actually show that in a certain sense this behavior is even generic. So they show that if you have a Brownian motion here and m is large enough, you cannot solve the equation for every starting point initially. So this is just perhaps to end. So I wanted to tell the story. I mean, I hope I'm motivated that these extremely singular SPDEs can be useful to quantum field theory problems. And this large field problem is very important because that's ultimately what one wants to do for these Markov chain Monte Carlo things. You want to run them for a long time. Short time theory is not good enough. So for 5.4, this is now resolved, but there are many other equations where it's not so well understood. And yeah, just in the end to show, I mean, in some examples now we can do it better than we could before. But I think I really like this example, which shows that it's actually a difficult problem. And there's still much to do. So I think I'll stop here. Thank you very much.
Thanks a lot. Yeah, thanks for the presentation. Are there questions? I see no questions. Maybe one question also relating, as you already announced, that it might be also related to techniques in the talk of Katharina Schratz. Is it possible here also to get an understanding using Fourier analysis and interaction of frequencies, or is this something completely out?
Yein. So no, actually, no, the answer is yes. Sorry, the answer is yes. So the techniques that work here for the parabolic, so it's kind of at the time when this whole business started, what I'm doing here is very much kind of pointwise real space, real space analysis in a sense, freezing of coefficients analysis locally around points, but at the same time, there was a parallel development by Gobinelli and collaborators that works more with Fourier analysis, para products, little with Paley theory or so, and to an extent in this parabolic world that that also works. But I think in the parabolic world, this pointwise approach is a bit more powerful. So it has turned out to be able to treat more problems and bigger generality. The story changes a bit if you go to wave equations or if you go to Schrödinger equations like we had in the talk this morning. So in those cases, these Fourier techniques seem to be, I would say, quite vastly superior to this pointwise analysis. And yeah, I mean, there's been amazing work also on these kind of things. And I think it's actually quite. I think Katharina didn't show one or two of the slides that she had somewhere that she jumped over, and there were trees that were also kind of, I mean, were done by a very similar set of people as this kind of stuff. So yeah.
Oh, thanks a lot. Are there other questions? Yes, Frank.
So is this a very general trend that you say the higher dimensions you get, it gets worse, and at some point there isn't anything anymore except something that is sort of trivial? Is that in a very, very broad context what you would be expecting?
I think there's different levels of answers here. So, I mean, the easiest answer, of course, is if you look at equations driven by white noise, then white noise, the regularity of the white noise gets worse by half every extra dimension. So this makes life harder in every extra dimension. So this is the easiest answer. So then, if you look at these kind of spin models or 5-4, I find it's a very interesting dichotomy because, I mean, in statistical mechanics, also often people look at these models on large scales, but they don't care on the small scales. So they would put themselves on a lattice and then look at the large scale behavior. And there, as you know, things become easier in higher dimensions. So you have sort of the triviality there. So it's a really bit funny that this large scale problem, in a sense, is easier on large scales, and it becomes impossible on small scales, and vice versa. Yeah.
Are there more questions? So if not, we will have a small break, and we thank our speaker again for the presentation. We have just 3 minutes